Predictive modeling and information. So a classifier is a function model. We have structured data with labels L equals C1 to CR, a feature space F, which is a subset of a vector space V. Could be RN or RM cross N, grayscale images, or color video, or many others. A classifier is a function from feature space into our response space given by this y1 to yr equals this function model, where the w's are parameters. When we predict labels, we tend to use one-hot encoding. So y1 to yr goes to 1, 0, 0, 0, that means we predict C1. If y1 to yr goes to zeros and then a 1, that predicts CR. Notice these are probability distributions, so it's a natural step to say that we're going to estimate a probability distribution on the classes for each possible value of the features. So y1 to yr is equal to p1 to pr, which sum to 1 and are greater than 0. For example, recall the iris data. So let's revisit a previous model, now predicting probability distributions. Here f was our latent space. Little f is now going to be a predictive model. That means that labels will be assigned probability distributions. Here's a point, and we assign it a probability distribution, where PR is a probability that the point is labeled by I setosa, PG by I versicolor, and PB by I virginica. Our decision surface doesn't have hard boundaries because we're not making hard decisions. We just have probability distributions. For example, if we have a point next to the actual data for I setosa, then we predict it's almost certainly I setosa. Farther away, we're not as confident, but we're still kind of red here, so good chance it's setosa. This is point in the green region is almost certainly versicolor, but on that place where the green and the blue kind of mix in, we're not sure. All we know, it's probably not setosa. Each of these numbers was greater than 0, and in each case the label summed to 1. And each is a function of L1 and L2, as you can see here. So let's look at the binary classifier as a predictive model. Notice we often use betas for the weights, just reminding you of that. So binary, there's only two probabilities, P0 and P1, and they sum to 1. And so we only need P1 since P0 is 1 minus P1. So our binary classifier is just a single response variable P1 equals a function model. And we often write P equals P1. Logistic regression, for example, is a binary classifier, as is the totally positive classifier. So totally positive means no information, independent of the features. The model extracts no information from the data. But how much information does the logistic model extract? In fact, what is information? What are we talking about? We have to address this question first. Knowledge, of course, we can say is that which we've already learned, and uncertainty is that which we do not yet know. Information is what we learn. The uncertainty we convert to knowledge. So first up, the amount of information obtained from the occurrence of an event is called the event surprisal. If an event always occurs, we're not surprised. If the sun rises tomorrow, no surprisal there. Only events with small probabilities of occurring can surprise us. If the sun explodes, we'll be shocked. So information takes uncertainty into knowledge. And we're going to define surprisal to be information from the occurrence of an event. Suppose the event is that a Q in a word is followed by U. That is, the sample space S, the set of all English language words, and the event E is the subset of S of all words with Q immediately followed by a U. For instance, here are some words in E. Well, this is no surprise. There's a high probability that if we see a Q, the next letter is U. That's a standard construction. But suppose we see a word with an XZ. Now that would be a surprise. Very low probability of such words. Are there any? Well, this, I'm not going to try to pronounce it, is a disease cats can catch from tick bites. And then there's some words that have XZ constructions in them. But it's surprising that we saw even one single word with an XZ. That is, surprisal increases as probability decreases. So let's look at this in terms of independence in information. Remind you real quickly what independence is. That's where the conditional probability of A conditioned on B is equal to the probability of A. So suppose me and you flip fair coins on opposite sides of the earth. A is the event heads for me, B is the event tails for you. A does not depend on B and vice versa. The probability of A conditioned on B is just the probability of A. The joint probability is the product of the probabilities. But let's look at this in terms of information. What we learn from A is independent of what we learn from B and vice versa. What we learn from what happens in China can be added to what we learn here in the United States. Independence implies the info from both occurring jointly is the sum of the informations from each respectively. Information from both coin flips, information from me plus information from you. So this is going to tell us the surprisal is a logarithm of probability. So let SI of A be the self-information or surprisal of a set that's a subset of S. So let's compare. If A is certain, its probability is 1, and there's no surprise. Its surprise is 0. If A and B are independent, their joint probability is the product of the probabilities, but their joint information is the sum of the self-informations. So we'll use this to prove that self-information is the negative logarithm of the probability of A for some base B greater than 1. Now to do that, we have to use the fact that g of p plus q equals g of p plus g of q implies that g of x is cx for some constant c. And we'll do this assuming g is differentiable. Notice it's almost linearity. We don't have the scalar scalar multiplication. The proof, I'm just going to run through it real quick. G of p plus 0 is g of p plus g of 0. So therefore, g of 0 has to be 0. And the derivative of g of p plus q is the derivative of each added together. And notice that the derivative with respect to p of g of q is 0. So g prime of p plus q is g prime of p. G prime of q is equal to g prime of 0. If c is g of 0, then g prime of q is c, and g of q is cq for all q and r. So, simple little proof. Now let's prove our theorem. We have to determine an f such that the surprisal, or self-information of A, is a function of the probability of A. So first off, we notice the surprisal of A is 0 if the probability of A is 1. In other words, f of 1 is 0. And that if A and B are independent, then the surprisal of the two jointly is the sum of the surprisals. In other words, the function of the product of the probabilities is the sum of the functions of the probabilities respectively. So f of 1 is 0, and if 0 is less than or equal to p comma q less than or equal to 1, then f of pq is f of p plus f of q. And if p decreases, then f of p increases. So this is probability goes down, surprisal goes up. So define g of x to be f of e to the x. Then g of p plus q is f of e to the p plus q, which is f of e to the p e to the q, which is f of e to the p plus f of e to the q, which is g of p plus g of q. Now we go to our lemma. G of x has to be cx for some constant c. So f of e to the x has to be equal to cx. But that means f of e to the natural log of x is c times the natural log of x. But that's just f of x is c log x. Also notice that p is between 0 and 1, and f of p greater than 0, since f of p increases as p decreases, and f of 1 is equal to 0. However, c log p is greater than 0, and log p is less than 0. So therefore, c has to be less than 0. So c has to be negative 1 over log b for some b greater than 1, the natural log. So f of x must be of the form negative log x over log b, but by definition, that's the negative log base b of x. So information, surprisal, is a logarithm, provides a natural interpretation of information. A decision is a question with only two possible answers, yes or no, true or false, so on and so forth. So here's my decision. For example, tails and heads being equally likely. My sample space 0, 1, probability of tails, probability of heads equals a half. Then I can find out what you got in your coin toss by simply asking you the question, is it a heads? And then you'll either say yes or no, true or false, and that will tell me what your outcome is. One decision implies two equally likely outcomes. 1 equals log base 2 of 2 is negative log base 2 of a half is the negative log base 2 of the probability of heads. So one bit of information, or surprisal, in the flip of a fair coin. So when we use log base 2, we say that the units are bits. A decision produces one bit of information. So a decision tree is a tree network where nodes are decisions and edges are answers. The root is the initial question. The leaf is the degree 1 node that terminates a decision path. So here is a decision tree with 4 leaves. So suppose we spin this spinner and we get equally likely outcomes of 0, 1, 2, and 3. So my sample space and my variable x, each outcome has a probability of a fourth. So the first decision is the question, is the pointer pointing up? Yes or no? Second decision, is it pointing right? Yes or no? And given those two decisions, we have enough information to determine all the outcomes. Two decisions can give us all 4 equally likely outcomes. So 2 is log base 2 of 4 is negative log base 2 of a fourth is negative log base 2 of p of x for all x equals 0, 1, 2, 3. So the event x equals any spinner outcome, the self-information is 2 bits of information. So we can encode outcomes with binary digits. So x 0, 0, 0, 1, 1, 0, 1, 1. And the 2 here simply refers to the base. So we have our 2 decisions, we get our 4 outcomes, and those 4 outcomes can be labeled by strings of binary digits. The same works in general. The information from an event, the surprisal, via the base 2 logarithm is information in units of bits. Now, surprisal, however, is the fewest number of binary decisions required to identify outcomes. Here's our spinner model again. Here's another decision tree, but notice that this decision tree requires 3 decisions for outcomes 2 and 3. We know we can do better. We know that we can do this with only 2 questions, pointing up, pointing right. So if S is a sample space and X and S, then the surprisal in the occurrence of X is denoted H of X. In other words, the event is just the single outcome X. So uniform distribution, suppose each outcome is equally likely, then P of X is 1 over R for all X and S. There's R possible outcomes. We say that P of X equals 1 over R is the uniform distribution on S. Notice that it's constant with respect to X. The surprisal is the constant function h of x equals log base b of r. Base b defines the units that surprisal is measured in. So 2 bits of information from spinner outcomes. X equals 0 means that the self-information as a function of x is negative log base 2 of a fourth. That's 2 bits. And notice 1 bit, 2 bits, that refers to the 2 decisions. Similarly, x equals 1, 2, or 3 gives us an h of x, which is equal to 2 bits. More generally, suppose x is associated with this set where r is 2 to some power d, p is 1 over r, uniform distribution. Surprisal is the fewest binary decisions questions that are necessary to obtain a value of x, which is this tree. There are d decisions, d questions to be answered, and that's the fewest in this example. The log base 2 of r is what d is equal to. Surprisal is d, negative log base 2 of 1 over r, which is log base 2 of r, which is the negative log base 2 of p. For all x, the self-information is negative log base 2 of p. For example, binary encoding. If we've got an 8-sided fair die, then here's my first decision, my second decision, my third decision, and those 3 decisions lead to my 8 possible outcomes, 0 to 7. And those can be encoded as binary strings, as you see here. 2 encodes as 0, 1, 0, base 2. 7 encodes as 1, 1, 1, base 2. There are 3 decisions. Is first digit 1, is second digit 1, is third digit equal to 1? And therefore there are 3 bits of information for each outcome of an 8-sided fair die. So what if we had a spinner with 3 equally likely outcomes? Well, now our probability is 1/3, so our self-information is negative log base 3 of a third, which is 1 trit. So if we use base 3, we call it a trit. A trit of information. And the decision would be a 3-outcome decision, left, center, right. 1 trit of information from 3 equally likely outcomes. But notice that in base 2, we would get negative log base 2 of a third, log base 2 of 3 bits. So in trits, it's 1 trit, but in bits, base 2, it's 1.58496 bits, approximately. So 1 trit is 1.58496 bits. We'll also often use nats. 1 nat is log base 2 of e bits, which is 1.442695 bits. So that means we can encode information as messages. Message encoded with an alphabet. Words are comprised of letters of the alphabet. We include spaces and punctuation and instead talk about messages made out of characters. Hello world is a message with 12 characters. The space being denoted by the underline there is actually a character. We can change to different alphabets. The simplest alphabet is the binary alphabet 1, 0. Messages are often encoded as binary strings. The length of a binary string is greater than the amount of information it contains. You don't double what can be learned from a book by buying another copy of the book. That simply increases redundancy, not information. For example, alphabetic letters and symbols are represented by binary strings in a computer. The Unicode string for I is 11010001. For N, it's 1101110. So the word independence as a binary string looks like this. But the information in a message is determined by the length of its shortest possible binary representation in bits. So the standard Unicode binary string representation of the word independence can be zipped, same concept as a zip file, which is smaller than the non-zipped file or files. So here's the Unicode representation of the word independence. Here is its zipped version. So what we do here, the zipping takes advantage of the repetition of the EN and the DE in the word independence. So the amount of information in the message independence is no more than 70 bits, but there may be a shorter encoding than zipping. So returning to classifiers as predictive models, we have now our function is giving us a response that's a probability distribution. And notice we'll often use vector notation. So if y is associated with L and x of I is an observation of x, then each one of these probabilities is the probability that y is the label c sub j, given that capital X is little x sub I, which is f of x sub I with those parameters. Training a classifier means finding a best probability distribution. Best probability distributions are the ones that are most informative. That is, we use information to obtain probabilities. We've gone full circle. Messages will give us information, will give us probabilities. Most importantly, information can be used to construct best fit probability distributions. The goal being to convert as much of the uncertainty in the training data into knowledge about the labeling. Indeed, algorithms learn how to make decisions that predict labels from observations of features. And surprisal is a logarithm of probability, which means probability distributions can be obtained using information theory.